15b, and this is very exciting again. And you might remember when we were doing 15a, we had this really long, elongated process. First principles, it's fun, it's very methodical, generates the right answer.
We haven't actually done 15a.
Oh, 15a? I think this is 15a, that's okay. That's okay, this is 15a. You might remember from 14d.2, we're doing that really long, fun, elongated process. Today we're going to look at a really simple way that you can do that in one single step. This is called simple differentiation. So, like maths, there's a long, complex way of doing it, and you do need to know that because in Year 12 exams they still ask first principles questions, and simple differentiation is what we'll use most of the time, but we do need to know that long process as well. So let's see if we can pinpoint what the rule is then. Okay, so up here I've got a summary. If this is our function, down here in this column I've got our derivative function. Okay, so here I've got, maybe we just ignore the first one for now actually, because that one can throw a bit of confusion in there, but if we've got x squared, it goes to 2x. If we've got x cubed, it goes to 3x squared, x4, 4x3, x5, it goes to 5x to the 4. You want to take a wild stab at what x to the power of n would be based on this pattern. Very, very good. Nx, n take 1, okay? This satisfies all of these, doesn't it, okay? That number comes out the front, and then the power becomes the number take 1, okay? So it becomes 3x to the power of 3 take 1 is 2, okay? 4x to the power of 4 take 1 is 3, so that's the rule. So if we have x to the n, then the derivative function is nx to the power of n take 1. That's amazing. So these are the rules we have to follow. Step 1, express everything as x to the power of n, fully expanded and at the top of the fraction. Okay, once everything is expressed like that, then you differentiate everything all in one step. Okay, and then we're going to simplify if we need to. So let's get into our examples here. We have x to the power of 7. Okay, so that means if this is f of x, it means, let's check we've satisfied all the steps. Step 1, express everything as x to the power of n. Yep. Fully expanded. Yep. At the top of the fraction. Yep. Okay, so it's ready to differentiate, and so we'll go f dash of x. Okay, f of x is the function. F dash of x is going to be the derivative function. Now, in the past, people have just, here's the problem, and then underneath they just write equals. Not true. This function is not equal to this function. We're performing an operation here. We're performing the derivative. We're differentiating. So we're going from f of x to, this is f dash of x. We must have this statement. Okay, if we've got x to the 4, f dash of x will be 4x to the power of 3. Okay, if we have f of x is 3 times x squared, the way we should think about it is it's 3 times and then in brackets x squared. So what's going to happen for f dash of x is this 3 is just going to hang out there, and then we go, what is the derivative of x squared? So it's going to become 2x to the power of 1. So that number comes out the front. X to the power of 2 take 1 is 1. Okay? And then simplify if required. This can be simplified to 6x. Here we are justified in just going straight from equals to equals because we've stated this is f dash of x, and it follows on from the previous step. Okay, if we have 5x, this one can be a little bit tricky, but nonetheless we'll apply the same rule. Okay, what we've got is we've got 5 times x to the 1. Okay, so that's my first step, isn't it? Make sure everything is expressed as x to the power of n. Now, when I'm going to differentiate this, the 5 is just going to hang out there. It's going to become 1x to the power of 1 take 1, okay? Nx to the power of n take 1, which is 1x to the power of 0. And we know that any number to the power of 0 is 1. So this is 5 times 1 times 1, or 5 times 1, it's just 5, okay? In fact, one of the rules that we've got written down, so we've got, if we have x to the n, it goes to nx to the n take 1. If we have kx, okay, kx is our function, the derivative is k. Okay, so if we have 5x, it goes to 5. If we have 7x, it goes to 7. Okay, you just drop the x off. Okay, now just some notation as well. Here I've got f of x. Okay, and because I've used f of x, the notation I'm using is f dash of x. Now in the book that in front of you, all of the examples are f of x. I should change some of them to y, which is why I've done it on the board here. Because you will be thrown both. Remember, they mean the same thing. But if we've got y, then the correct notation for the derivative is dy on dx. Okay, here's the function, here is the derivative function. Okay, we've got this is the function, we differentiate it, this is now the derivative function. Okay, now we're getting to a stage where we should start following our steps. Express all as x to the power of n. So in this example E here, I've got the square root of x. I haven't expressed it as x to the power of n. So what's that going to be as a power? Square root of x?
X to the half.
Very good, thank you, Sophie. So that's going to be x to the half. We've expressed it all as x to the n. It's at the top of the fraction. We're ready to differentiate, okay? And we're going from y, which means we go to dy on dx when we differentiate. And it's going to become n x, and then to the power of n take 1. I'm going to write this one out slowly because there's a bit going on there. N x to the power of n take 1. Okay, and so that's just going to stay as half x to the power of half take 1. If you have half take 1, that's going to be minus half. Okay, it's like 0.5 take 1 is minus 0.5. Okay, so you're going to get full marks like this, okay? I'm going to give you full marks there, but I just need to prepare you because in the back of the book they may simplify it a bit more, which means what they'll probably do, okay, is they'll probably write it as half times, now x to the minus half is 1 on top of x to the half, right? So they'll put it at the bottom of the fraction using index laws, okay? Negative power means it can go to the bottom of the fraction. And then x to the half is a square root. So that would simplify to be this, all right? I'm going to give you full marks there, okay, but it can, the back of the book, they'll probably write them like this. Okay, they'll probably simplify it like that. Okay, so that's good. We've done here, we've introduced a number of different ideas. Here we've got a number of terms, okay? And that's fine. When we're going to differentiate it, we're just going to differentiate all of the terms all in the same step, okay? So we've got to express as y. Have we, let's check, have we satisfied our first step? Express everything as x to the n. Yep, it's fully expanded. Yep, there's no products in there other than that 5 out front. And it's all at the top of the fraction. So we're ready to differentiate. So, because it's y, it goes to dy on dx. Okay, and I've said that any numbers there are just going to hang out the front. Okay, so we've got 5. And then in brackets, we've got x to the 4. So the derivative of x to the 4 is going to be 4x to the power of 3. Okay, so we've differentiated that term. We need to differentiate this one now. We're going from minus x. Now this is a little bit of a tricky one. Okay, remember I've said if you have kx, the derivative is k. Okay, so over here we've got 1 times x, which means the derivative is 1. All right, so we have minus x, it goes to minus 1. And then lastly we have a constant. Okay, and a constant's very easy to differentiate. Anytime you differentiate a constant, it's 0. It disappears. Okay, a number just disappears. So this is our answer, and we can simplify that as well. 5 times 4, 20x to the power of 3. Take 1. Okay, so are there any questions at this stage? All right, I'm going to spin the board around. They're getting a little bit more complex. So we've got everything expressed at the top of the fraction. That 5, okay, there's a number of ways we can think about it. I think the best way to think about when you have a number at the bottom is that this is 1 on 5, x to the 4, take x. Okay, so you can think about that. That's just a number that's multiplying x to the 4. Okay, we can do that, that's fine. It's still equal to one number. And notice how I've gone, here's f of x, here's f of x. We're ready to differentiate. So now, f dash of x. Okay, f of x, let's differentiate. So this 1 on 5 is going to hang out there. And then we're looking at x to the 4. If we're differentiating that, that's going to go to 4x to the power of 3. Okay, nx to the power of n take 1. And again, we've seen we've got take x. So we've seen the derivative of kx is k. So if we've got 1x, that's what we've got there, isn't it? If we've got 1x, the derivative is 1. Okay, so this is going to go to take 1. And it can be simplified a little bit. We have 1 on 5 times 4 is just 4 on 5 next to the 3, take 1. All right, so we're very clear. Here's f of x. This is still f of x. And then we're differentiating, and here's the derivative simplified. Okay? Now 4h, okay, we've got everything expressed at the top of the fraction. Everything's expressed as x to the n, but we need to fully expand it, okay, which means here I'm going to need to perform a perfect square expansion before I can differentiate it. So here's f of x, and then here is f of x again once it has been fully expanded using the perfect square rule. It'll be 9x squared, take 2 times, I'll write it out to show you the expansion, and then plus 4 squared. So what's that, 6, 24. Okay, so look how clear we're being. We're going f of x, f of x, f of x. Everything is at the top of the fraction. Everything is x to the n. We're ready to differentiate. And we must differentiate all in one step. Okay, so everything's ready to go, and then we do it to every term all at the same time. And the better you get at this, right, okay, so you might look at that and go, that's going to be 9 times 2x. Okay, so you can look at that and you can go, if you can see what it goes to, you can go, that goes straight to 18 to the power of x. Okay, here we've got kx, so it just goes to k. And then we've got a constant which disappears. So this is the derivative in the simplest form. All right, and you're going to get to a stage where you look at that and you go straight from there to there. Okay, but if you're still a bit unsure, I encourage you to follow, expand it out, do every single step. Okay, let's have a look at I. We've got 3 on top of x to the power of 5. So first we need to express everything at the top of the fraction. So that's going to be 3x to the power of minus 5. All right, so that's just index law, so I've brought it to the top of the fraction. That's still the same function, that's still y. And now we're ready to differentiate. We'll go dy on dx. It's going to be, the 3 is going to hang out there. We've got x to the minus 5. So that's going to become n x to the power of n take 1, minus 5 take 1. So that's, 3 times minus 5 is minus 15, x to the power of minus 5 take 1, minus 6. Alright, so again, I'm going to give you full marks there. They may write it like this, minus 15 on top of x to the 6. Okay, so we're very, very clear. Here's y, here's dy on dx, and then we're simplifying. Okay, so we differentiate all in one step. Okay, we're going to get a few like this, okay, where we have these sort of fractions and we can't differentiate straight away because not everything is expressed at the top as x to the power of n. But one thing we can do is we can split the numerator. So if this is f of x, right, another way we could write it is like this. It's x on x squared plus 5 on x squared. Let me explain to you why that's okay. If we have 1 on 4 plus 2 on 4, okay, they have the same denominator, which means we can perform that operation. And you can see that it simplifies to 3 on 4, but perhaps the intermediary step is that it's 1 plus 2 on top of 4. So that's what we're doing here. We're doing the opposite. We're starting with 1 plus 2 on 4, and we're going back to, well, we could write that as 1 on 4 plus 2 on 4 because they have the same denominator. So we've split the numerator. Okay, and then we can simplify this a bit. So it's still f of x, So this is going to become x on top of x squared. That's 1 on top of x. Okay, so I'm assuming that we've got a good grasp without index laws there. If it's an area you need to work on, let me know. I can provide some stuff. Plus 5 on x squared. Okay. So what have we done so far with that one? We've gotten rid of the denominator, but we need to express it at the top of the fraction. So 1 on x, that is x to the minus 1. And 5 on x squared is 5x to the minus 2. The 5 just hangs out in front of it. So look at what we've done here. Okay, we have not done anything yet. All we've done is just manipulated it. Twisting it and turning it and smashing it and pulling it apart. We haven't changed its value whatsoever. This is still the exact same function. If you graph that and if you graph that, they're going to be the exact same on your graph. Okay, but the point is now we've got it to a stage where we're ready to differentiate because everything is expressed as x to the power of n. Everything is at the top of the fraction and it's fully expanded. We're ready to go. F dash of x is minus x to the minus 2. Okay? Minus 1, x to the power of minus 1, take 1. And then plus 5. That 5 is just going to hang out. Minus 2x to the power of minus 3. So we'll simplify it and then we'll even put it at the bottom of the fraction. Take 10x to the minus 3. Okay, so I'm giving you full marks there. They'll most probably represent it like this, but very clear. Here's f of x, and then bam, we differentiate f dash of x. Okay, and the next one's going to be the same, it's just a bit more complex. Okay, we've got y, we need to split the denominator, so just because of shortage of room, I'm going to take up, I'll go a bit sideways, I think. So we'll split the denominator, and straight away, I'm going to convert cubed root of x to x to the power of the third. And then over here, we've got to take x on x to the power of the third. Okay, so these x's have the same basis, which means we can do the top power, take away the bottom power. So I'm going to write that operation up before I perform it. Okay, so it's still the exact same function. We have the 2's just hanging out there. We have x to the 4 on top of x to the third. It's going to be x to the power of 4, take a third. The top power, take the bottom power. That's index laws we learned in year 8. And then the same here, x to the power of 1. Okay, if there's nothing written there, it's a 1. So let's perform that. So if we have 4, take a third, what's that? That's 12, take a third. That's 11 on 3. Take x to the power of 1, take a third is minus 2/3. Okay. Point is, still the same function. Okay, you graph this, you graph this, you graph this, you graph this. They're all going to be the exact same, but it's at a stage that we're ready to differentiate. It's at the top, everything's x to the n, it's fully expanded, we're ready to go. dy on dx. 11 on 3. So n x to the power of n take 1. Alright, so even though it's a sort of odd number, 11 on 3, it's just the same rule. N, x, n take 1. And then the same here. Take. Okay, so I'm writing this one out. I'm using plenty of brackets just so we can be really clear about where negatives go. So look, that negative is just hanging out there. And then I'm just focusing on when we differentiate that, that's what it goes to. Okay, now we're ready to do a bit of simplifying. That's going to be 22 on 3 x to the power of 11 take 3 is 8. And then over here we're going to have plus 2 on 3 x to the power of minus 2/3 take 1 will be minus 5 on 3. Okay, so some pretty complex fraction operations there. Don't be alarmed by those. The point is the process, isn't it? Get y by itself in a form ready to differentiate and differentiate. That's what we're interested in, is can you perform that? So there is one more question to go, but I think I want to leave it for a little bit. Maybe we can come back and do that towards the end of the lesson. I would just like you to practice this skill. Okay, so there's lots of questions there, lots of repetition. By the end of the lesson, we're going to be pros at it. Let's do it. 15A.